Welcome to the Meltzone Podcast. It's been a while, but this is episode 73. I'm Tom.
And I'm Stefan. And on today's episode, special episode, Tom's going to talk about that later. I quickly going to talk about my trip to Cologne yesterday, trying to find new products that we can put on our store. We have a bit of chat about threaded inserts and threaded insert testing, and a quick story how I tried to hunt down my TikTok imposter.
Yeah, and Stefan teased it is a special episode. The majority of today's episode is going to be a chat with E3D, with two of the engineers from E3D about extruder testing, about what they look for when developing a new product and how it differs from how I and maybe Stefan test products. So that's very interesting. Enjoy the episode.
I got up yesterday morning, 3 a.m. in the morning, then took the car to Ulm train station. Then we took the high-speed train, the ICE, to Cologne. And then we were the whole day on the International Eisenwarenmesse, iron products exhibition. Basically a huge exhibition with 1,200 tool makers that make like screwdrivers and everything. And we were there the whole day until 5 p.m. and then took the train back to Ulm and then car back home. And I was just so super exhausted.
But
it was interesting.
That sounds rough. I did get an invite by a company to that show as well, but I declined because I didn't have the time.
Yeah, I don't really have the time either, but we basically wanna get just like more stuff in our online shop, and we basically thought about either flying to Shenzhen at some point this year and talking to a couple of like manufacturers, or take the opportunity and just take a train to Cologne and talk to some of the vendors right there. And it was really interesting. Initially, I thought, okay, do we really find someone who can produce tools in the quality that we want to have? But after a lot of walking and a lot of digging, I think we found some really interesting suppliers.
Nice. I guess you're not going to go into more details there. Like companies producing for other companies often tends to be sort of an open secret where you can tell, hey, this is made by these guys. And I mean, you tend to be pretty open about what you're selling and what it actually is. You don't make any false promises there. I still find it funny when people like point out to my threaded inserts video and they're like, yeah, cool. That was basically an ad for Stefan's inserts. And I'm like, I mean, he sent me some inserts. Yeah, sure. And they performed well. Like, what am I going to say?
Yeah. Well, maybe just for the listeners right here, I didn't know that you were producing that video, and I was kind of shocked at the moment when you released it. And I thought, oh shit, I hope that our inserts performed well.
Yeah, they're good. I mean, they're good inserts. Do you need them to be as good as they are? I don't know. They are good and they're reliable and they're consistent. So, and they're fun to set versus the much cheaper injection molding ones, which
exactly.
I am planning a follow-up on that entire video just to have a bit more of a repeatable test setup to separate torque and pull-out forces or pull-through if I insert from the back. I do want to have a bit of a more beefy tensile testing machine, essentially, which I've been meaning to build for years now. So we'll be doing something that's a bit more consistent there, and there will be a follow-up, including your inserts again.
It's an interesting topic, and as you also just mentioned, we never said that this is like a proprietary design we came up with. These are basically catalog parts, and this is the reason why you can also get them from other suppliers all over AliExpress and Amazon and whatnot.
Well, I mean, people were specifically saying, hey, why are you not including the Rutex inserts, which are like the other popular brand that you can get in Germany, which is basically the same insert that you have.
Exactly. I guess they perform basically the same. The only thing that we basically make is, for once, say, okay, if people that are interested in threaded inserts have the option to buy inserts from a random brand on Amazon, but if they can get for the same price the inserts also from us, and in a way also support the channel this way, and we make sure that they have proper quality, and we do QC and source them and whatnot, we just encourage them to support us in this way and not just give their money to like a random company. So in that regard, we don't make something special yet. Maybe in the future maybe in the future we want to see if we can further increase the performance of the inserts, be it that they are just stronger in plastic. I don't know, but developing something like that takes a ton of time and takes a ton of money, and I'm definitely lacking time. And of course, you need to invest a lot of that. And if it doesn't pay out in the end, it's not really worth doing it. They're good enough. Let's put it this way. Yeah,
they're great. What I am going to experiment with is just doing different kinds of inserts. So I've already got probably a dozen different types of inserts, which are the typical helicoil, which is just a square wire threaded in to form the shape of a metric thread on the inside. Solid threaded inserts, which have metric threads on the inside and outside. Wood Rampamuffen, the coarse thread on the outside. So some that you don't melt in, but some that you actually screw in, and you create the negative for those in your part. Just experimenting more there, because I felt like having a printed part actually have the perimeters and interlock with the infill more by having that thread sort of in the plastic in the perimeter. That actually did add a bit of strength. In the end, my results were like, hey, the perimeter pulls out of the part. That was the result. So getting something that is stronger there may just improve performance overall. And also, if it's easier to set, if you don't need a special insert tool, or if you don't need to use a soldering iron, whereas you can just screw them in, that could also be a benefit. So haven't worked on that video yet, but that's coming up for sure.
Let's maybe quickly talk about something different. So at the end of last year, I was contacted by a couple of guys telling me, hey, there is a TikTok channel, basically, I don't know, auto ripping off your YouTube videos and putting these in portrait format on TikTok.
Was it actually? So here's the thing. I've seen tons of services that do like AI video editing and AI auto whatever. I've tried a couple and they suck for the most part. Was that actually a value add that the imposter did, or was it literally just we're cropping in the video and we're uploading it in 18 chunks to TikTok?
Well, they were cropping and also cutting it down so that it was shorter. I can't really tell if it was done manually.
Probably not then.
Or if they did use an auto service, just like AI-based something. But the thing was, in the end, I think at that point when I first noticed that they had already like 10,000 subscribers on TikTok, I filed a copyright claim. TikTok didn't care for 2 months. I tried to contact them. They just blocked me. And initially, I didn't realize that, because when I, after that, checked their TikTok page, for me, it looked as if there were no videos on the channel.
Oh, right. So the channel blocked you, not TikTok.
The channel blocked me. The channel blocked me.
Yeah. Isn't that the same strategy that like the YouTube scammers used to do, where they actually block you, the video creator, but still have their comment out, so you don't see it, but it's still visible to everyone else?
Yeah, maybe. It was weird, and then, now like over 2 months later, I thought, okay, let's do this another time. The channel significantly grew. It already had like 40,000 subscribers on TikTok. But the weird thing was that I didn't initially realize why they were doing this. So I thought they're just putting affiliate links everywhere and in that way monetize it. But then I talked to a couple of bigger TikTok creators and they told me that this is something pretty normal, and the intent right here is not to make money with affiliate sales, but to basically use my content to grow a TikTok channel, and then at some point just either rebrand it or basically use it to scam either viewers or other companies and tell them, look, this is my TikTok channel. I'm that big, and please send me free stuff.
Okay, well that's a bit more sinister. I thought it was going to be like the which you see with Amazon product swaps, where you have something that gains popularity and that has good reviews, and all of a sudden the product is something entirely different. Same with same thing that happened to Matthias Wandel recently, where his entire channel got taken over twice now. And essentially he was doing the work for the scam. It's the same thing that you're describing on TikTok, where you have a channel and you yank all the content and you put your own scam stuff on it, and it has an audience. Okay, that's not great.
Maybe so at that point I filed a copyright claim a second time. Nobody cared again, but then I was lucky and got in touch with a YouTube viewer who said they're working for how's the company called behind TikTok? ByteDance, yeah. And they were able to basically forward my request internally, and then after a couple of days, the channel got deleted. It's going to be interesting if they take the content that they already did and just start a new CNC Kitchen imposter channel.
Does TikTok have like a content ID sort of thing, like YouTube does?
I mean,
not like we're eligible for content ID anyway, because we're way too small. But there is sort of not actually. YouTube does have the duplicate videos, re-uploads. It does detect that for creators. So TikTok does not have that, where you can claim your own content and then it's like, hey, this is mine.
It's way harder to do that. So I actually had to file a copyright claim with my with all of the documents that this is my brand, this is my YouTube channel, with my full address, telephone number, and
right.
But
I mean, it does open up an opportunity for you, where it's now been demonstrated that there is interest in that sort of content, in like simply edited down versions of your videos. So why not do that yourself?
And I'm looking into that. I'm actually looking into that. So my first idea was, so if TikTok would not have taken down the channel, to just rip basically the videos from their channel and put it into my TikTok channel, which is existing but doesn't basically have any content in there. I thought about if this was copyright infringement as well.
Under what law? Like, what jurisdiction are you looking at here?
Yeah. So this is the thing. So I already started downloading some of the TikTok videos from them and just thought about putting them on mine.
You should just do that anyway, because like it's your content.
But so kind of my problem is that I want to be happy with my content, and just stupid edited down shorts are not something I want to be known for.
It depends on the market. Like, if you're on TikTok, if that's what the people want, then give it to them. The same with my two recent videos. Like, you can still see like the Magneto, perhaps maybe a bit in frame behind me, and the, what did I do before? The E3D, the 72 euro printer before that. Those were videos done in an incredibly quick and dirty and like random way almost. It was more of an exploration of, hey, we're going to discover this together. We're going to unbox this together. We're going to see what works, what doesn't. If there's weirdness, you guys get to experience it. And people love that sort of stuff. Like my last two videos were 1 of 10 by a long shot. Like these are performing so incredibly well. It's like, okay, I would be stupid not to make more of those, right?
And this is the hard thing. So if videos where you put a ton of work in don't perform that well, and these simple formats perform so good, it really begs the question: what should you do in the future? Do you want to continue doing these basically first looks onto weird 3D printers or weird products, which is basically you're able to film that in like an afternoon?
Well, yes, but then it takes a couple days to edit because it's a lot of content and it's a lot of really tight edits that you have to end up with. So it is still a bit of work, but it's something that you can do much more easily than an in-depth review of a machine that is like, if I were to do an in-depth review of the Magneto, that would be heaps more work. The kicker for me was that I started watching, and people have realized this in the YouTube comments. David does tech stuff. Basically, he does the exact same stuff for computer parts. He buys a weird laptop off of AliExpress. He buys a pink graphics card and builds a PC around. He buys whatever weird hardware he can get his hands on and just does and experiences that hardware with the user. And then benchmarks it and does a couple of things there. But that same sort of exploration I found really interesting to watch. I found that just something that's enjoyable. Maybe, it's not the same sort of value as a full review of, that Tech Power Up does with someone or Gamers Nexus does. It's not, it's an entirely different type of content, but it is still something that is, to an extent, educational, but fun to watch, right? It's entertainment. And in the end,
you kind of have to adjust to the platform, and if people enjoy that more, if the platform kind of gives you the impression that you should do more of this because it's catered to more viewers, why not take advantage of that? In the end, you've initially been known for your in-depth reviews and stuff like that, but if that is not performing for your channel, for your business, why should you put even more emphasis on that?
Exactly. It is something that I do want to do, but it's also very exhausting because it's just a ton of work. So if there is simply, and this is sort of the content that I've been looking to find, like something that is less work than a full review, but is still valuable in some way to viewers, right? So I've got I've got one more printer now and another one that I may grab that sort of fits that initial look bill, and I guess we can see more of that. But I don't want to do just that. So but like we announced in the intro real quick, we have E3D as a guest in this episode, and that is a rather long recording that we managed to do, and we chatted about extruder testing standards. It is rather long, I do need to warn you, but it's rather enlightening to see what they are looking for when it comes to developing an extruder, and how they sort of disagree with, or agree and disagree with how we tend to do testing. So here is that interview for you guys. We've got two guests here, Sam and Mike from E3D, to talk about the Revo Roto and sort of like your engineering process about this. So I did some benchmarks on this, and it works. It works, but I feel like we had some sort of different views on the product, right? So let's maybe start out with like what your design goals were with the Revo Roto.
Sure, I guess this originally started as a bit of a brainchild of Sanjay, as so many E3D products have. His entry came through holding a Chimera, saying how big and heavy it was, and he was like, I want this, but I want it smaller. Obviously, there's a lot more to it than that. Yeah, I guess got them for...
Yeah, I've got both of them here. One's mounted on an aluminum plate, but yeah, there is a very definitive weight and size difference.
There is, yeah, and essentially it kind of like spiraled from that and stemmed into multiple research projects into different types of drivetrains, into different motor options, and loads of things like that that then culminated into the project, which I guess the tagline of that was to make it smaller, lighter, same print quality, if not better, and also making sure that it can be easily integrated into the newer systems that are coming out, where the speed is kind of I guess we should clarify, motion speed is kind of the new thing, because this speed can be used for lots of different things, yeah. But that's kind of where it started.
Yeah, so we've got this. It really is an exceptionally small, light, compact extruder, and there's sort of two design choices that are interesting. So the first one is the 3D printed cooling shroud mounting plate, centerpiece on the front, heatsink.
Heatsink. Yeah, that's what we ended up calling it. Yeah.
So that is. Well, I mean, Bontic have been doing 3D printed front plates for a while. What was the thinking behind using 3D printing for this? Yeah, it's ultimate freedom of design choice, right?
Yeah, but we actually had, so way back when we started the project, there were other ways we were considering going with it. We looked at getting like a little magnesium casting. We looked at machining a heatsink object out of, just literally machine it out of billet. Tried all different things. Machine from billet's obviously good for prototypes. And then which
essentially, I do have the smart orbiter here as well, which I did compare to in my video, and it does use just a machined heatsink, right?
Yeah. And then we had a few different things going on in like the design process, and then we were all sat around in a meeting room one day, and we were like, you know what, we've been like talking about this idea of using 3D printing to do the heatsink for a little while. Not as a joke, but as a like, it would be really awesome if we did this. And then there were a few things in the design process that led us to just like check where we were and like evaluate everything. And we were like,
and I guess there's certain features that were starting to become an issue to making other methods. The obvious ones is it's got the 6 and a bit. Well, I say a bit because one of them's not a full fin. There's the 6 fins that rotate around the heat break. Like that, they're only based like a mil apart, and they're a mil thick. And like going to a machinist and say, "Please, can I have a few thousand of these?" And they look at you and go, "No, no." And so there's aspects like that, and then also things like the air brake, which I guess is not one that's spoke about that often, but there's a bit of air that comes back through underneath the heatsink as a bit of a shield to stop any of the heat coming off of the heat coil getting into the heatsink in the first place. But we were essentially starting to realise that traditional manufacturing methods were starting to become the reason that we were stopping iterating the cooling performance, and we didn't want to be limited by that, especially because we're in an industry that the whole point is you have ultimate design freedom.
But in the end, so in my normal job, I work a ton with metal additive manufacturing, and I know the costs for printing even parts out of aluminum, which is still pretty steep. So you guys obviously have compared the costs of like conventional manufacturing, even though if it's like really intricate machining with die casting and with additive manufacturing. And you still came to the conclusion this is the right process for that, and it wasn't just, okay, let's flex right here and make something that nobody else has done.
There's a bit of both. We did speak to like the partner who's doing the subcon printing for us. We're not doing that in-house, in case that wasn't obvious. And one of the big things that kind of got them excited about like buying into it was that we came in saying, for this to be viable for a product, like extruders cost, like in this this ballpark, this is roughly how much people will pay for these. There are lower cost ones, there are more premium ones, but you can put a pretty small like wrapper around all of them. And so for us to be able to make it work as a product, we need to be able to buy a finished heatsink for this amount or less. And they were getting excited because they kept getting customers coming to them asking for like one-offs and two-offs and things for aerospace. But there was no great examples of like mass production in their specific like area yet. And it's almost like a case study for them of like, look, we can take this awesome manufacturing method and use it for production scale, which is done, but not really. It's not done very much at the moment. So I think that kind of, we wanted to push that, and yeah, obviously it's not the cheapest like piece of the bomb.
No, but even comparing against the other manufacturing methods, especially like the machining, which is probably the most obvious one to get something of that intricate shape, we were still having to, even to be in the same ballpark of price, we were having to do some compromises to the design for what we felt was
and it was heavier.
It was heavier, yeah.
Yeah, because we're down to about 1 mil wall thickness almost everywhere in the printed part.
Yeah.
Whereas we couldn't hit that with machining.
And things like the skeletonizing the sides, like you can just, there's no impact or cost for that.
Yeah, so the 3D printing process, it does scale to a certain extent, but probably not as well as like a magnesium die-cast does. Like where you invest in the mold and then their part is pennies. This still has a high per part cost, even if you're doing tens of thousands of them.
But I guess on the molding side is an interesting one, because then there's the like aggregating, like yes, the parts might be a lot cheaper, but the tool definitely isn't, so it's not just as cut and dry as what is the part cost. And the other thing is it's a UK company, so they're a couple of hours up the road, which means it's great for partly shipping, and also we can drive up and down in a day if we need to go and have a chat, discuss any upgrades we want to do and stuff like that.
Yeah, and of course, with not having any sort of a mold, any sort of investment for that one specific geometry, changes are relatively easy. Like I assume there is still a bit of tweaking going on to get this part to print as it does. Similar to having like a no, that's actually molded. Similar to programming your CNC toolpaths, right? Where the machine is going to run anyway, but you have that initial startup cost of getting it started. This doesn't have as much of that versus the mold.
When you print hundreds at once, like when you print your first 10, you put them all in the middle or something, and then when you print hundreds, you've now got the whole chamber full of parts, and then making sure that everything's dialed in when you get the parts out of the corners and the parts in the middle and all that kind of fun. There's still work to do. There's still fun and excitement.
Yeah. And then the other unique design choice is the combination of the extreme dual stage gearing and the 0.9 degree motor. So how were those choices made?
Especially considering that you were targeting high-speed printing.
Yeah. So we started with the approach of what is optimized gear ratio that we want. That was the number one thing. And something that we've sort of spoken about in our blog is that through that testing, we kind of started to refer to it as a torque to force ratio rather than just a gear ratio, because the gear ratio emits the hidden ratio of your hob diameter. Because what you actually care about is the force that is coming force on the filament, right?
Linear force on the filament versus the torque that the motor has to produce to get to that force.
Yeah. So we sort of like, as I guess it's a bit of a side, but we sort of like looking at it from that approach, and we created these sets of gearboxes that had loads of shaft holes, and you could interchange gears, and effectively we could tweak the gear ratio with a pretty fine resolution in order to be able to see what impact on the force speed curves and like torque drop offs and things like that of the motors and hot ends were. So that's kind of where we started. I feel like I can hear you wanting to.
No. Yeah, I think fairly early on we're looking at a combination of the multi-stage design. As Sam mentioned before, we did a bit of a research project into like what type of transmission do we want to do. Like there was one point which like it was a concept, but didn't get any further than that, where there were like 5 spur gear pairs like stacked up next to each other, because that you could also achieve the same thing. And it goes on a whiteboard, and then you're like, no, we're not doing this for other reasons, right? So settling on the planetary and then like a second stage spur reduction, that happened as an output of like the pre-concept work, if you like. And that was then looking at what we could do with that and a load of different motors.
And yeah, I guess on the motor front, I guess the 0.9 point, I guess the reality there is that we did test 1.8 and both 0.9 motors. We've got a giant old box full of them from various manufacturers and different lengths and inductances, all that stuff you'd sort of expect. And we settled on that one because we were able to maintain the force output that we were after at the motor speeds that were required, and ultimately that was the criteria. And that's kind of how we ended up on that motor. It wasn't a like, don't use 0.9s because of the large gear ratio. It's like, well, if we can get the thing to function at those higher motor speeds, even if it is a 0.9 and the higher separates, then that's still okay from our point of view in terms of the output is the main thing.
Yeah, because the motor, we were choosing a motor based on like it needed to have the right output, but there were then like other little things that you would like. There's a normal print speed, and you don't want the motor you've selected to like whine with a horrendous noise at the speed that everyone prints their infill or something like that. There's a lot of other little assessments like that, and it. I guess taking it a step further, I think we've probably shared this before, I don't know, but it's a shorter, the stepper motor is not an 18mm stepper motor, it's also not a 13mm long stepper motor, it's halfway in between, it's a 15.5, which essentially we had made custom, because when we were doing a lot of the initial work, the 18mm motors, they had enough output. The 13mm ones didn't have as much output as we wanted. It's not just a question of force output. Oh, you can up the current and then you'll then generate more heat, which has other negatives. So it's like balancing all of the levers and dials at once. So yeah, we worked with a motor manufacturer and made that like Goldilocks motor as a reference, like kind of let's tweak a few things specially and put it in the middle. Because yeah, it worked with the 18mm motor, but it is a significant mass penalty to do it, and you can't like tout the benefits of your taking 0.5 mil out of your wall thickness of your heatsink if you then just add a load of extra motor on the back. It doesn't work together.
Yeah, but so that brings me very smoothly actually to sort of the bigger picture that I want to chat to you guys about is like, where is the operating point for these extruders? And I need to go on a bit of a tangent here to sort of get to that bigger picture. Is what I tried to do here was to measure or to generate a comparable, measurable performance number of this, and I realized there is not one number. So if you compare that to PC benchmarking, computer parts, GPUs, CPUs, you can benchmark a video game. You can run that. You get your FPS number. You get your 1% lows, and that is a definitive number because if you play at 1080p, then that's what you're gonna get. There is no such thing with 3D printing because there's such a wide range of both materials, speeds, temperatures, print setups, layer heights. How did you guys arrive at at your benchmarking setup, because it obviously differs from mine, because there are some different results there. What was your target?
So I guess in terms of the setup, and I guess we have, probably not going to be much of a surprise, but we have a similar version of a force rig for,
we call it a force rig.
We call it a force rig for measuring force output, as well as like encoder data that's strapped on there, and that is something that we use in the like research phase, because that is great for like direct comparisons between setups. But I guess on that point, in terms of the curve and the numbers that you got in your testing, we don't actually disagree with your numbers. The only thing where our view on that changes is that the point of actual real-world printable with that nozzle and material setup is not at the top of that curve; it's lower down the curve, which means that you can reach the flow rate that you want for that nozzle setup. So it means that it passes on that. But then, in order to be able to analyze, say, a 0.8 nozzle, or to analyze PET-G with the 0.6, or any other configuration, as you said, there are somewhat infinite of them. You then need to get that specific force curve, because all of the plots don't follow the same line, somewhat as I guess you understand. And so we create like a cloud of data is probably the best way to describe it. So we'll sort of run very similar tests, but we'll do that with multiple different setups, and then we'll get lots of dots all across the force speed curve. And I guess where we determine that dot then transitions to real world printing. So we would then do a flow rate test to determine the maximum achievable printing flow rate. And then you go to your graph, and then you find your point, and then that's your point for that graph, and then you repeat it. It's obviously quite labor intensive to get all of those points. And then you want to look at make sure that your extruder, that's a new one, your extruder is then above all of those points, to be able to compare across. I guess that's how we do that in the research phase. Is that?
I think where I guess if we're talking about that data set for a minute, we're using the approach on Roto that we essentially want the extruder motor to stall after you've exceeded the point of it's not good printing anymore. Right. So if you're working to avoid the thing where you have to I've stripped my filament because something happened, like I had a jam in my spool feed, so then my dual drive hob started munching through the filament, and now I can't drive my filament anymore, so I'm going to take my whole thing apart and clean it out, and that whole issue. If you shift the failure mechanism for the extruder to not chew your filament but instead stall the extruder motor, then that's a recoverable issue. So if you fix your tangle, if you've got the right logic and everything set up and it pauses your print for you, you can then recover and you can carry on. So in order to achieve that stalling failure point, to be completely clear, you can't make it do it for absolutely every filament, because there's crazy different hardnesses and stuff. For the majority of what customers are going to use, you get that stalling failure. To do that, you need the output to be there so that you get the output of your particular hot end. We call them nozzle hot end material combo. You need those three things together, and there's a flow limit for that. You need to be able to output that force, but then if you go much further, you want your motor to stall.
And there needs to be a little bit of headroom, so that if there is a sudden little spike in force, or you don't have your filament path is 3 meters long or something arbitrary, it can compensate for those without stalling out sooner. But yeah, I guess that's where that ethos for Roto specifically.
So then when you're looking at a hot end and you're trying to pick where that is, if you use an extruder that's got a massive motor on it like a Hemera, and it's just got a huge headroom of force, there'll come a point where you do a flow rate test I don't know if did you create it originally, Stefan, on your original YouTube video, but the one that's everywhere now, you've got testing, like.
I think I also kind of stole it from Bondtech.
Yeah. Oh, of course. Yeah. But we have a version of that where we've tried to add some other geometry into it. We'll do a test with like our nozzle hot end material. We'll make sure that the hot end is definitely going to be the bottleneck, as in that test has got like a full fat mirror on it. And then we'll see the point at which real world printing stops. And then we're like, that's the limit for that hot end nozzle material combo, which is the stuff we publish on our website. And obviously with our release cadence, we had Roto still in development at the same time as High Flow, so we could link all that together and try and make it all work seamlessly.
So essentially, what I'm sort of summarizing here is that you don't actually see the need to have, how do I put this? Something like a Chimera, like the original non-XS Chimera, this is going to be overspec'd 100% of the time, and it really doesn't matter that this has more push force than a Riva Roto, because it's not something that you would need. How do you? My follow-up question that would be: how do you compare extruders then, when one is good enough and the other one is also good enough, and then what is?
Yeah.
How do you determine which one is the better one? Aside from like, yeah, this one has the rotor mount and this one has a standard V6 compatible hot end.
Yeah, and I guess on that point, like the rotor, with it being small and light, it's obviously focused towards small nozzle sizes, because when people there's a lot of discussions about high speed printing, but you need to have the distinction between high movement speed printing and high flow printing, because you can have high flow printing that involves high motion speed or high flow printing that does not involve like bigger nozzles, right? And if you're wanting to move your motion system fast, you need to have the lightest, smallest package on there. I mean, it's one of the reasons why like Deltas have Bodens and stuff like that, so that it get reduced like print artifacts. But on that scenario, so that's why Roto is focused towards like the 0.4s, the 0.6s primarily. Yes, it will work with the bigger nozzle sizes, but at that point you don't need the lower mass, if that makes sense. So there's like also products like Super Volcano, which we still do, which is a Chimera product. So there are like, we traditionally talk about in the hobby space, like this portion of the graph, I don't know, I'll show you around, the camera's going to show it, but this is like traditional print speeds, but then you can have the crazy, sorry, Mike, like higher flow ones that are more industrial applications off to the side. But
yeah, I think that what you said there about how do you know if your extruder is like, how are you comparing them? Can it print the flow rate is like a tick in the box. What we're trying to focus on, because we think the customer cares about, is like print quality. Like ultimately what the user cares about is the quality of what's coming out of the nozzle. So from an extruder evaluation point of view, a large amount of what we do is what is the quality coming out, like what print artifacts are coming out.
So what differences are there that an extruder can make when it comes to print quality? Because to me it's like either it grips or it slips, and as long as it grips, like the extruder is just out of the equation for the most part.
So like one of the things we did with Roto, I suppose there's two ways to look at it. There's, if you take one unit, what is the print quality of that one unit? And then also when we make hundreds and thousands of them, what's the variation in print quality unit to unit, which are subtly different questions. One good example is for like the final drive stage on Roto, you've got a few very precision machined it's like bores in the heatsink. So you have a pin pressed into the heatsink which has a very low eccentricity, like running bushing with one of the two drive hobs on it, and that's controlled in the same component as like the idler pivot. And they're like, when we did our drawing for it, they're datumed one to the other. The like center distance there is controlled as tightly as possible, so that when you get one, it's consistent. And There are other designs out there where like two ends of a shaft are controlled in other parts, and that allows things to be off square and different to each other. And then, like, coming back to the bushings, I guess you've got the old school method of attaching your 20-tooth dual drive gears to a shaft was like with a grub screw. There's some really great videos online about the impact of that, the eccentricity you cause by tightening the grub screw, and look, you get like a pulse. So every time your hob rotates or your dual drive gear rotates, your center distance is essentially varying subtly, and you get like a speed up and slow down of the filament speed with a revolution. And I mean, well, Sam and I, printing is near ruin for both of us. We love it, but every time we look at a print, we're like, oh, that's got the thing in it that we spent like 2 years trying to design out of roto.
But for us as reviewers, basically, what kind of metric would you use to judge something like that? Of course, you could look at the prints, but is this something you could see either with an encoder, or you should even see variations on the extrusion force if you use an extruder at like at the performance level where it's happy?
I guess the force rig setup that we were talking about earlier, it does have some limitations, and primarily it's around like resolution. Now, we have spent a lot of time and effort and money trying to make ours as, I guess, all singing and dancing as it possibly could be. But even that, there's noise in that, and you then always have to refer back to what does it actually print like. So all of our static testing is primarily done at the beginning of a project to do general qualifications on, is it compatible with this? Does it, like, what is the output force of a range of speeds? And as I said, we do that with like using different nozzle data points to be able to get to the different points on the graph. But then as soon as the further we go down a product development cycle, the more that transitions to real world printing. So for example, the beginning might be, can you get a print out of the extruder? That might be the initial thing, and it's like, great, this thing prints, let's get some data and some values to baseline it on our comparative tests. But then as you move through, that split changes, and you go to, let's just check this thing is still outputting the force it should be outputting, but then let's go put it on a printer, run through a myriad of tests with various different materials, including flexibles and things like that, so that you can check stuff like retraction capabilities. You can check things like smoothness of extrusion, as Mike's saying. The eccentricities, the big issue there is that you then get pulsations in your filament. Now, a lot of gearboxes that are manufactured, doesn't matter if they have pulsations. An example we use all the time is wing mirrors on cars. You know, like when you park up and they zoop, boop in. If that motion isn't completely constant, does it matter? No, as long as it gets to the end point, you've got there. And so the tolerance.
Well, if it's on a premium brand, you might hear it that it's like not going, but it's going like, that's something that could be controlled for. But like in general, yeah.
But what you really want, like, I say it all the time, Sam's going to laugh at me again now, but the one of the buzzwords that we talk about is like precise metering of extrusion. Like, I want to go at exactly this speed for this amount of time, and I want the variation to be very low. So when I command it, I don't get this sinusoid, or like the reality could be that you get like 6 or 7 of them all stacked up on top of each other. Because like for us, we've got a multi-stage gearbox, and we had to do a lot of work to make sure that we aren't getting print artifacts from anything. You've got like gear pairs that have all got different tooth counts. You've got like the shaft eccentricities, and then you've got the frequencies of all the different stages all combined together as well. And all of them have got like a pulsing speed relative to the output of the extrusion. And it does just come back to final sign-off for us is real-world testing, and not just on the one that we fettled by hand to prove the concept, but like take one, do nothing to it from the production line, test it, does it output what we want it to? So you're probably right in that there is a an aspect of trained eyeballs looking for things that we don't like. We do have, as you probably would imagine, we've spent a long time writing a lot of this down and lots of pictures of this is nasty and we don't like this. If you see this, it's caused by this, or this in-house test print is the one that you run to check for this problem.
And as you go through cycling, you like hone in that, because there's a fun little artifact that we found during Roto that was caused by people walking heavily near the printer, which is really hard to debug, because a print overnight would be fine and then you'd come in and do it the next day. And essentially the rigidity of the printer wasn't rigid enough, and so when someone walked, the table would wobble and then the print head would doop into it, and then you'd get...
And if it's just 100th lower, then you do see that.
There is no frequency to that. It's just whatever the person jogged through the office. And so
we were like trying to count the distance between the artifact and this amount, and then it turns out that you were on a suspended floor in an industrial unit, so that when someone bounced through the office with enthusiasm, you can see it in your prints.
Yeah.
So there's all sorts of nonsense there.
Mm. But do you see the necessity for kind of standardizing certain tests? Because I have the feeling that for the last couple of years, every manufacturer is throwing around numbers, and there's basically no way to compare them. You don't know if they have been printing their PLA at 300 degrees Celsius or at a reasonable 210 degrees Celsius in order to tell you that their hot end is better than the one from somebody else. I've been thinking about for ages if there's the necessity to kind of define standard materials, a standard PLA, a standard PETG, a standard ABS, and then kind of temperature settings or something like this in order to make sure that manufacturers have the opportunity to kind of comply with a set amount of specifications, and then can say, okay, per basically these settings right here, our hot end, our extruder performs this way. I don't know if this is something that manufacturers want, because this might show that their product might be inferior. But for me as a reviewer, I think there's a necessity for something like that.
To a certain extent, that also opens up sort of the chance to over-optimize for those certain benchmarks. You've seen that in tons of areas as well, where it's just we're optimizing for this one specific test. Euro NCAP crash test, for example, where it's like our benchmarks are like our cars perform extremely well. They get 5 stars, but then in the real world they fold up. So yeah, where do you see that?
We talked about this quite a lot, I think. The thing that's missing is the disclosure of the parameters in the first place. So like the final step, as you said there, might be that everyone has to use the same PLA. But a step back from that is just tell everyone what PLA you used, what temperature did you print it at. Something like your layer height as a proportion of your nozzle diameter. If you make a lower and lower layer height, you get like an increase in back pressure in your system. So if you don't standardize it, if you have like a really high layer height, then if that will even skew your data compared to someone who's done it at a more conventional one. So when we do internal testing, we try and keep the test parameters as close to what we would use if we actually printed the print at the end of it that we're all just wanting to make. Try and make as many of the parameters be that. And then the key thing is to just disclose all of that information. So you could go, like the list could be very long. We could start a list that has like probably 50 things in it right now if we really wanted to. And if someone then published some data where they had used one thing wildly different to everything else, like print temperature was really high, then obviously not everyone's going to spot that, but people that are critically reviewing the data are going to be like, hang on, this test parameter was different to everything else that we're looking to compare. So from an E3D perspective, I think disclosing the information is the most useful thing we could do.
I think you've tried to do that when you released Revo High Flow with kind of publishing the data, which is, I think, a very good approach. But I'm really thinking about if some people, either from the, I don't know, review community or even some manufacturers, sit together on a round table to kind of establish some standards there, because people are lazy, and only a very small minority will notice that some of the test data, even if they just publish everything, is skewed or different to what other manufacturers use. And this is just opening so many possibilities to kind of adjust your test results in a way that they look favorable for you.
Yeah. And also the other side of that coin is us as sort of reviewers who have to sort of compress the performance of a product into something that is palatable for the average viewer. We have to make most of this stuff up on the spot, right? We have to invent test procedures essentially. And typically that means it's not comparable between, like, if Stefan does a video and I do a video on something, even if it's something as simple as a 3D printer. That's the most complex thing we review, where there's tons of degrees of freedom.
I guess.
But also, like, what I try to do with the Revo Roto is, because I'm making stuff up on the spot and I'm thinking about, like, how can I test this and how can I, like, show differences between products, I need to test multiple products in the same way. I need to put them through the exact same testing procedure, and it creates overhead. Like, it doesn't allow for, like, a standardized set of test data, like, again, PC benchmarks. If you have a PC Mark 2017 or whatever it is, you could compare that with someone else. Here you can. So Stefan, I'm sorry if I like extended your original question there a bit too much. What would you like to see in sort of a standardized setup, and what are we missing today?
So I think for me there are, like, a few key aspects. What you would, if I was going out and I was going to buy an extruder, what would the things that I would personally care about, is what I'm trying to think about the other day. And it's hard to get away from the topic of flow. It's there. It's an important one. And so flow from real world print testing, so that you can compensate. So you can have a look at, like, what's the layer adhesion going around a tight corner. Are there any, like, pulsating artifacts that you can, like, that stack up when you actually have a like a track, rather than that not being there, or just, like, gaps in extrusion that are just a bit easier to spot. And then the other side would be thermal performance, which I think sometimes it might not be the coolest, but that would be a really bad pun. Sorry, but it might not be the biggest topic, but it's a really important one, because fundamentally, if your thermal performance is poor, that's going to be your biggest issue with your system. And that's something we spend a lot of time on. And then the other aspects would be
maybe just a short pause right here. Can you maybe just say 2 sentences what you mean with thermal performance? Is it like the gradient between, like, the Meltzone and the extruder, or yeah?
So thermal performance in our testing is, well, one of the thermal performance tests is elevated temperature. So what ambient temperature does your system perform without jamming? And again, that is perhaps another can of worms of, you could choose a print that isn't going to jam. I mean, I could print a vase and there's no retraction, so it's probably going to be pretty good. Which is why when we do that, we have these towers, lots of very small towers, that it does a really small extrude and then it retracts. It does it over and over and over and over. It's essentially just trying to force heat creep. And then we put it in an enclosure that we can control the temperature of, and we set it going, and then we leave it for a day and come back. Well, we don't actually just leave it for a day, but the test is to print for that long, to say that it can perform at that temperature. So that might have been a bit long-winded as usual.
Okay, thanks. Something just to come back to that is I would be curious to see whether you guys agree, but when we've done our like flow rate benchmarking as well, something you said about like if you guys both did essentially the same video, you still might not get the same results. Something that we have seen a lot, if you take Revo High Flow as an example, is someone will be like, well, I've set the flow rate of my printer with these nozzles installed to be loads higher than what E3D's data says is fine on the website. And then you'll get commentary around, well, I'm getting much higher flow rates out. And maybe if you're just printing infill, then you can't tell that you're full of extrusion artifacts or you're getting massive under extrusion because you're not properly melting your filament anymore. So I guess what I'm trying to say is internally, we are very strict on those tests. Like if you do one where the flow rate increases as you go up in like Z height, as soon as you see that transition to something not being exactly the same and perfect as it would have been at lower speed is the point that we're calling it done. Whereas there will be customers who maybe more entry-level users, they don't care about smaller little things that are creeping in, but we don't want to say that our products are capable of those things necessarily, because for us, we deem them as like a poor quality. But what that creates is a difficult metric to maintain for everybody, because if someone just wants to say that they can get 70 millimeters cubed a second through a hot end, but they don't care what it looks like when it comes out the other end, they could theoretically do that.
And this is I don't know, are you two guys gamers at all? PC gaming?
No, not really. Sorry.
Okay. Then I guess this is going to be more to aim towards the viewers and listeners. So, again, circling around to PC benchmarks. And Stefan's laughing because I've talked to him about this before. There are two big brands in PC graphics cards, AMD and NVIDIA. Yeah. And those two don't necessarily compete on performance, but they also compete on features and quality. It used to be the way that, your graphics card renders an image and it can do so many images per second, FPS, right? Now, though, there are upscaling technologies. So NVIDIA has DLSS, AMD has FSR, where it'll actually render a lower resolution and then upscale it with AI algorithms or whatever, temporal upscaling, blah, blah, blah. And the results that NVIDIA gets are consistently a bit better than what AMD gets. So now you're sort of shifting that balance where how much of the faster, how much performance gain are you willing to take, and how much quality are you trying to trade off, or are you willing to trade off? And that's something that PC reviewers are starting to struggle with. I've seen Hardware and Box talk about this, where it's like, hey, these two, we can't really compare them anymore. So you guys are basically saying, okay, as soon as there is any noticeable degradation, then that's it. Whereas somebody else may actually be willing to take a bit of that degradation if it means we get 50% more speed out of it. Should that be something, should there be something that we test for as well, where we have to sort of find a point of equal degradation in quality, sort of, where we're pushing it past the point where it's perfect? Is that something that you see viable at all?
One of the... Go on.
You go after. I think it's a very interesting one because, as you say, it is very application specific as to what is good quality. But I think if you are trying to circle back to standardizing the testing to make it as regimented, then I guess we are still talking about the flow because it's quite an easy one to approach. But you should have a standardized track, because there's many out there, and like ours is subtly different and to others as well. But there should be standardized track, layer height, width, and the material one I'll get onto in a sec. But and then as Mike said, it should just be like any imperfection, because of the way that different extruders are limited, then you might get a different failure mechanism. If you're printing that track, for example, Roto is designed to stall, so you could suddenly get a stall and it just doesn't extrude, whereas a Hemera, stuff's still coming out. It doesn't look very nice, and so they might have failed in different mechanisms, but the failure point is still the same in terms of like end user from our perspective of what is a good quality. So if we're trying to just standardize it, my view is kind of like any print imperfection that, I should say, any change in print consistency, because as long as it's consistent going up, when it stops being the same, that should be the point. But then
is there such a point? I mean, Stefan, you've done extrusion amount and slippage testing, and if I remember correctly, you found that there isn't that it sort of starts gradually slipping, and there's not one.
Exactly. I think it's really hard to pinpoint this point of failure. So in the end, there still needs to be some wiggle room, but in a way, we kind of need to say, okay, 5% under extrusion is still acceptable. Is 5% still acceptable? And I think only with these objective metrics is it possible to objectively compare extruders. In the end, is an objective comparison. Do we kind of get all of the metrics with an objective comparison? And even the applications even the applications of these extruders might be different. Somebody might be looking for print quality. The other one is looking for strength, where these limits might be totally different. So it's really hard for us, especially if we want to do a good job reviewing a product, to make sure that we are getting everything and we are happy with our work. And even you as a company say, okay, this was objectively right. We might not be happy with the result, but at least they did a fair job.
Yeah.
And by the way, talking about like standardization, it's just full accident that I've got the linear motor magneto behind me here, where all the rules about, hey, this needs to be lightweight, completely go out the window because there's no elasticity in the linear axes. It just rips, and you could put whatever the tool head on here is crazy heavy. That also starts shaking things up. But yeah, just wanted to point that out. That's not there intentionally. It's just from the last video still.
Yeah, no, definitely. I kind of feel that the step one is like consistency with an entity and transparency in that. What I mean by those comments is like at E3D, we do our flow rate tests in the exact same way. They're all real world printing, which I guess, as we've been sort of stressing, is that's what we do for an end product, is real printing. And we have our guidelines and we publish those on our website. I can't remember. It's got a copy of the track and it's got the parameters that we use. And so like, that is like sort of stage one, and then you guys might have your own, but you might not have access to the same filament that we have access to. I mean, we do use Prusament for that, but it might be difficult to get, might be out of stock. But as long as that is then consistent with your testing, I feel like that's the initial step that we kind of need to get to, and then becomes the job of trying to tie them all together and like say, oh, we like the way that this is being done by this individual company, university or whatever, and we're going to make that the one that everyone is trying to converge towards. And then hopefully you end up in this beautiful utopia where everyone's printing the same test tracks. But I feel like that's unfortunately probably not just around the corner.
But I think it's already a good start that you start publishing stuff, because only this way makes you transparent, and maybe others are following that, which makes it easier for us to maybe understand your results better, but also to make it more comparable to customers. So maybe think about if you disagree with some tests that are out in the wild, to just release your test setup so people can replicate that. I mean, the idea behind scientific papers is to write everything down that somebody else can perfectly replicate that. And in a way, even though I'm not writing academic papers, I try to make sure to document things that these tests are repeatable. And if we're not doing that, we will never end up at the point where everyone's happy.
I mean, it doesn't actually serve anyone any real benefit from like a company side. If we publish a load of data that is ultimately based on rubbish tests that have turned the temperature up too high to get a bigger flow or something like that.
And it's changed the trap weight, or we've like tuned the extruder, or like anything like that.
It won't last long. People are not going to take that data if like the whole community just says, well, this doesn't work.
I kind of disagree here. Because there is only a very small minority. Maybe it's we get that more and more that people are trying to test these kinds of claims. So I still think it serves many companies still at the moment very well to kind of play around with their numbers and tweak their tests, that the test results look positive for them, because I think a large majority of the customers will not notice these differences, and it's good for their sales numbers. And even if something comes up, oh, that doesn't work, for many companies, I think the damage is kind of minimum. I highly appreciate that you have the impression that it would not serve you well, but I think that is not something where everyone would agree.
Yeah, I suppose.
At least internally.
Yeah, there's obviously different, like, there's a whole spectrum of companies in existence. Like, we obviously supply extrusion systems into OEMs for factory fit machines, but we also, a big part of our business as E3D is selling you essentially an aftermarket upgrade. And if we sell you an aftermarket upgrade and then the aftermarket upgrade doesn't improve anything, then that's subtly different to perhaps if you were to just buy a stock machine off the shelf, for example. Like, as a whole integrated system, there is obviously we do a bit of that as well, supplying things into OEMs, but I don't know, maybe that barrier is higher in the sense that an aftermarket upgrade, are people not more likely to get found out when it doesn't offer an improvement? Does that make
right? Because there's always the chance that the user screwed something up, that it didn't configure something correctly, or the machine doesn't support it fully. There's always that uncertainty to it, right?
Yeah. I mean, it is, and I guess to go on that a bit more, it very much depends on what machine you put it on. Take a roto, like I can't remember off the top of my head the numbers, but like the 0.4 high flow, like with ASA, for example, I can't remember what that number is. Say it's 28. That feels maybe the right, no, 20. I don't know. That's not the point I'm trying to make. Say that is what you can achieve with that roto, but then you throw it on a Voron Trident and you have it enclosed, and it's got big beefy bed, it's got side blow, like it's all the bells and whistles. It's nice and enclosed. It's a fast motion system that can take advantage of the lightweightness. It's got things like input shaping, and so on that, then yeah, you can get to because you need to not forget that volumetric flow is really important for comparing, but your motion system has to be able to keep up with the XY relative speed for that. And so that machine would have no issues with printing at 300 millimeters XY speed. With
as long as it's a layer height that is small enough to not exceed the flow rate limits of your extruder hot end combo, right? So you can. Yeah.
And then so that's all great, perfect. They've got all the results that we expect them to get, that they expect them to get, but then you put it on a different machine that isn't traditionally designed to move fast, then they're limited in other ways, and so they're like, oh, well, this can't do what it does. And it's like, well, there's a bit of an intricacy there, because the extruder then isn't the limiting factor. It's another thing has become the limiting factor, which I guess is just there's another
another example of the same thing there is if you've got an extruder that has a low force output, then if you put on a hot end that has a really long really long melt zone, for example, then you might have, I don't know, it's like a volcano or something. You've got a volcano nozzle hot end hanging off a fairly low force output extruder, then you're getting and flow rate, and then you might change to a high flow Revo system instead. And I don't want to give a specific example because I don't want to make any numbers up, but like there might be a Revo high flow nozzle where we rate the absolute flow rate for the same orifice size is slightly higher than a volcano, but perhaps the required force to get it to achieve that highest flow rate is slightly higher. If you then do a direct swap on your extruder and your extruder doesn't hit that force output, then you're now going to perceive that your new upgrade hot end isn't as good as your old one because something else is creating a bottleneck that you're not aware of, because as a customer that's not really thinking about all the intricacies in the system, they're just like, well, I only changed this. It's like, yeah, well, as you change from one to the other, there are different things that are affected and it's got different requirements of the rest of your system. Does that make sense? A bit?
Yeah.
All silence. No? I can go again.
It did to me, but we talk about this a lot, so I...
Yeah.
It's complicated.
Yeah.
I guess.
Let me have one more go. Let's say that the absolute force required to extrude at the critical flow rate, the limiting flow rate, is higher on a particular Revo high flow nozzle as it is on a volcano. So both of them can achieve the same flow rate, but you need slightly more extrusion force to do that. And that might be a result of the internal flow splitter geometry, or the fact that the volcano's got a longer melt zone, so it drops the force, things like that. So if your extruder output is above the force required for the volcano threshold, but it's below the force required for the maximum flow rate of the Revo system, then you're going to perceive when you swap one to the other that you can't hit the limit anymore.
Yeah, when you go from Hemera with Volcano to a Revo Roto Revo. Oh, which way around is it? I can't remember.
The Revo first, right?
If you change two things at once and they should be equal on paper, but they're not, then yeah, you still have those two variables that need to interlock and meet up at that same operating point. And if they don't, yeah.
Or if you change one and it then shifts the bottleneck to a different part of your system that you didn't touch, because you think that it's fine, but it's not. Sorry.
Yeah. So maybe to close this out, I'm perhaps getting the impression that it is a little more complicated than what we as sort of independent third parties are able to deliver and to manage to pack into a review. Like what I tried to do with Revo Roto and the benchmarks there was already sort of the capacity and the time investment that I'm able to make for a single piece of content. Yeah. Looking at having to do multiple materials, having to do temperatures, real world testing under specific benchmarks with different test prints, measuring for consistency, which, yes, maybe something that you can automate with an encoder. I do have some thoughts there. Is where sort of can we, Stefan, myself, other people who are trying to inform the customer and help them make a proper decision of whether this is the right product for them or not, where is the value that we can add? Because doing the full benchmark suite, as you guys are doing, seems to be beyond what we can do for like I said, a single piece of content.
Yeah, and I think the thing there is probably circling back to what I was talking about earlier, of step one being consistency and transparency of an individual entity. And so as long as, I guess for the flow rate, we have a track, and yes, they might be subtly different, but as long as, Tom, you're consistent with what's the cutoff, what you just say is a failure point, and Stefan, you do, and then we do. Hopefully, again, we'll converge in the future. But that initial consistency, because I think for comparing between different products, what's the most important thing is having consistent setups for doing that, rather than looking at E3D's results for one test and Tom's results for another extruder and set. Like, that is all well and good, but we're not quite at that point where they all do necessarily match up exactly. But in terms of the testing, it's, yeah, you got your flow rate, then like things such as retraction capability, so like better spikes, like, yes, you can tune them in, but they are something that should be looked at. Can you tune it in a reasonable value? I mean, eventually, like, it's almost comical to say, but it's a great test print. Like, it was designed to...
Yeah, not agreeing there, disagreeing there at all, yeah.
It's really hard to say, like, to choose something else if you just want to, like, do that covers a lot of aspects, but... And then you've got your, like... Do you want to do like a functional print? Because some people are, they're not here doing intricate models, they're doing functional, big, bulky objects, which you can test things like layer adhesion on, or fitment of parts. So like, what is your like extrusion with good and stuff like that. And then you've got your cosmetic side, where you can print these like incredibly intricate busts and figurines and things like that to see how they handle the small fine details and
dynamic performance of the setup.
It coming back around to what makes a valuable review is ultimately like, is the person watching it, do they think that it's useful to them, and is it going to inform whether or not it's a worthwhile thing for them to buy? Then if I think for us, it's always going to keep coming back around to like the actual print and print quality. Like so for us, we've spoken a lot about the flow rate testing, but the stuff that we really tried to nail down was really showcasing, like, we've made the print quality great, and we've maintained, if not improved. Well, I'd say we've improved over Hemera for sure.
Which is like talking about like smooth surfaces and like nice seams and that kind of thing.
So yeah, using the example of a review of a roto, if we were to publish like a test procedure, it's not all just going to be numerical data, because what the customer, we would hope, wants to see is that if they install it, they're going to see great print quality. And the print quality is not just what do the walls look like, it's also like, can you turn the speed up and will it continue to perform correctly? Can you turn the temperature up and is it not going to jam? And those are all like within print quality, but it's like for us, it's about the end quality of what the customer perceives. So I think while the metrics that we can gain off of the test equipment are very useful, what the end customer really cares about is what comes off their build plate at the end of the print.
And I guess just to add to that as well, that is obviously step number one, because if you don't have a system that prints badly, you're just never going to give it a chance. But then there's the second part, which is like, what is it like to interact with as a product? So which is where we try to add the features of like the bistable idler, so that you can do it with one hand and it locks out the way, and there's an integrated filament sensor and a temperature thermistor and like all of these usability features, so that like you can disassemble it with the same size of Allen key and it's like 3 bolts and it's off, and then you can put it back on without square nuts and stuff like that, like falling around. So there's kind of like a barrier to entry, which is, does it even print okay? But then there's all these other things of what extras do you get as that package? What other things does it enable you to do, really?
But does that create a problem in the world where, I guess, if you're trying to showcase stuff to a big audience, then if you just print a benchy with it, theoretically, like, say we send out like 20 or 30 rotos to loads of different people that are going to publish a video review, if every single person just prints a benchy with it and goes, look, a boat, people will watch whichever one they see first, and then there's no reason for them to watch another one, which creates another problem, right?
That is a whole different topic on its own, which I'm running into constantly, but really doesn't have much to do with the product itself.
No.
But yeah, there's always going to be people looking at a product from slightly different angles. Again, coming around to the PC industry, there's sites like The Verge who do like this is the product and this is what it's like using this product. And then there's other pages, Tech Power Up, Gamers Nexus, that really do comparative testing and that focus more on the numbers. And I think the same with 3D printing products and media outlets. It's going to be that same divide where some focus more on the measurable stuff and some focus more on the user experience, like, with the Roto Revo, where it is a Revo system, where it does have the sensors built in, that sort of thing. Aesthetics, I mean, that's something that some people care about too. Maybe me not as much with a part that goes on a functional machine. But yeah, I think that's the beauty of having sort of independent media outlets, whether it's people on video platforms or written articles. I mean, we have Tom's Hardware also doing stuff like that. It's the beauty of having a diverse landscape of really independent outlets there, who can all focus on different areas, and then whichever one the viewer, the user, aligns most with and sees the most value in, that's the one that they're going to consult.
Yeah. And as long as whichever outlet or platform or whatever that is ultimately always brings, whether it's cosmetic like photos and videos of results or whether it's like data, as long as it's explained what that data means to you as the person trying to use it, what that actually is. It's not just a game of top trumps necessarily. Like having the highest output force in the market doesn't matter to you as the end user, because as long as you've got enough output force, then you don't need any more. For example, that making that distinction and then using the same approach to look at other products is perhaps the way it's useful.
Right. Okay. Yeah, that's a good conclusion. Yeah. All right. So Stefan, unless you have anything to add?
I think we rambled already too much. So I think it's good. I think both of us, Tom and me, need to think about if we need or should adjust our testing method. I think it was some valuable input. We might not agree on everything, but it was a pleasure getting your view on this. I mean, from engineer to engineer, it's always good to get that insight, and let's just see what we end up with, and maybe there might even be a standard for some kind of testing in the future.
What there will definitely be is comments under this episode on YouTube with people voicing their opinions, and for anyone who's, especially on YouTube where you can leave a comment, for anyone who's watched this thing, I would very much be interested in hearing your opinion as well. All right, so with that, thank you both for your time.
Yeah, thanks. It's been good fun.
Yeah, I'm excited what E3D comes out with next.
Thank you.
It's always going to be something fun.
Cheers.
All right, thanks, guys.
All right, thank you.
Thank you.
Cheers. Bye.
Cheers.
Okay, so like I said, if you guys have any feedback on that, definitely let us know, because this is something that we're both sort of trying to figure out. And I think that was some good feedback from E3D. Stefan, what about you? You look fried.
I look fried, yeah. So I appreciated the feedback, and if you guys have any, put it down in the comments. And I think we gonna call it a day.
Pretty much for today, yeah. So thank you, Stefan, for the time as well. Good having some time to chat again, even if it was a rather special episode.
And a long break in between.
Yeah, should we do the next one a bit earlier than like in 6 months? Because we have so many topics written down. We've crossed them out.
Next time. Yeah, thanks for your time. And I hope to see you again soon. And thanks for listening. Thanks for watching. If you want to support us, there are links down in the description. And we will see and hear you in the next one, hopefully soon.
All right. Bye.
Bye-bye.